These are the notes for AP Calculus on the topic of slope fields continued. So we've got our differential equation. This is what the derivative dy dx equals. And it says on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. So this one, notice, is not one where you can easily set the numerator equal to 0, denominator equal to 0 to find your horizontal and vertical tangent lines on the slope field. So sometimes you just have to substitute the points in one at a time, and not really a easy shortcut on it. So let's see how that works on this one. So make a little table here to organize the information. You can do this on them, or if you can do it in your head, that's fine too, whatever works best for you. So we can substitute the points. You can start wherever you want here. Let's say we start with, well, first let's label our columns here. The x coordinate, the y coordinate, and our derivative dy dx. So let's say we start at this point here at negative 1, 0. Negative 1, 0. If x is negative 1, that'll give us a negative 1 half. And then y is 0, so that wipes out that term, so plus 1 gives you 1 half. So right here, you'd have a slope of 1 half. So picture going up 1, right 2, headed towards this point. And you don't have to be perfect, just do it as close as you can to it. Then let's go ahead and substitute in the origin 0, 0. So 0, 0 wipes out both of those, so you're just left with 1. So the slope there is 1, 0, 0, up 1, right 1. Up that. And then if we substitute in 1, 0, you get positive 1 half. 0 wipes out the next term, plus 1 gives you 3 halves. So that would be up 3, right 2. So a little steeper than this one. Like that. So you can see as we keep going to the right, it gets a little bit steeper. So if there's not an easy pattern to follow, but it is a pattern you can kind of see. All right, let's take a look at the next row here. So if we put in negative 1, 1, well, that's going to be negative 1 half. And then minus 1, plus 1. So the negative 1 and positive 1 cancel out, and you're just left with negative 1 half. So that'd be down 1, right 2, headed towards that point. Then if we substitute in 0, 1, 0 wipes out the first term, we end up with negative 1 plus 1 gives you 0. So that's horizontal. So you still might have some horizontal ones, but what we won't see on this particular slope field is any vertical ones. Notice because we don't have a denominator here, so this will never be an undefined slope, but it could equal 0 like this one does. Then if we substitute in 1, 1, we get 1 half minus 1 plus 1. So the 1's cancel out there. You're just left with 1/2. So that has the same slope as this one. So halfway there. Now let's substitute in -1, 2. So I'll give you -1/2 minus 2 plus 1. So that's -2 plus 1 is -1, -1/2 minus 1, that's -3/2. So that would be from here, it'd be down 3, right 2, about headed towards that point. Then if we substitute in 0, 2, 0 wipes out the first term, we just end up with -2 plus 1 gives you -1. So that'd be down 1, right 1, headed towards that point. And then 1, 2 will give you 1/2 minus 2 plus 1. So that would be a -1. Combine those, 1/2 minus 1 is -1/2. So that'd be the same slope as this one. Down 1, right 2. So you can see the pattern follows on each of these rows. As we move to the right, the slope is increasing. So this is getting less negative here. Here it's -0, then positive. Here it's getting more positive. So you can see that kind of a pattern that can help you see that your slope field's consistent at least. And then last row here, -1, 3 gives you -1/2 with x, and then -3 plus 1. So the -3 plus 1 is -2. And then -1/2 minus 2, that's -5/2, -2.5. So that one would be down 5, right 2. So notice this was -3/2, so a bit steeper than that one. And these don't have to be perfect, just relative steepness we're looking at. And then 0, 3. 0 for x wipes out the first one, so you have -3 plus 1 gives you -2. So this one, it's kind of in between these two. This is -2.5, this is -1.5. So -2 down 2, right 1. Like that. A little less steep than that one. And then finally 1, 3 would be 1/2 minus 3 plus 1. So that's a -2, -3 plus 1, and then 1/2 minus 2, -3/2. So that'd be the same as this one. So getting a little bit less steep here. And again, you can see they get a little less negative as we head this way. All right, so there's our slope field. And remember, this shows you kind of what each of these are like mini tangent lines. If the graph were to go through the point, what would the tangent line look like? So I can kind of give you a general idea of the shape of the original graph that has this as the derivative. All right, now let's take a look at part B. A little review on this one. It says let f y equals f of x be a particular solution to the differential equation. Remember, this particular solution is just the original equation that has this the derivative with this initial condition, which is the point -4, -1. But notice it doesn't ask you to find the particular solution. It just says let it be the particular solution. If you had to find it, remember those are the ones where you'd have to separate the variables and integrate both sides, plug this into solve for C. But you can see that even if you try to do it on this one, it's not really easy to do because notice the x minus y, it's hard to separate the variables on this one. So you need a different technique. Separating the variables wouldn't work here. So what it asks though is not to do that, to find that. It asks, does f have a local minimum, a local maximum or neither at this point where x is -4, and then justify your answer. So notice this one, when the derivative has both x and y in it, you can't really use the first order test and draw your number line, put this on here, because there's no other points we know that we can test, and we need both the x and y coordinate in order to test it into the derivative. So the first derivative test doesn't work here, so the only option we have is the second derivative test. But remember, the first thing we have to do with the second derivative test is actually substitute this point into the first derivative to see what we get. We substitute that in. X equals -4, and y equals -1. That'll give us 1/2 times -4 minus -1 plus 1, which simplifies to being -2 plus 1 plus 1 gives you 0. So because the first derivative is 0, that means it's a critical number. That means it could be a local minimum or a local maximum. Remember, where the derivative is 0 or undefined are the places where you could have a local minimum or local maximum, same as a relative intermax. And this one would never be undefined. And for the second derivative test, it has to be 0 for you to be able to use the second derivative test. And it is. So this means we can move on to actually find the second derivative by taking the derivative of this using explicit differentiation. So the derivative of the first derivative is the second derivative. We write d squared y dx squared. The derivative of 1/2 x is just 1/2. Minus the derivative of y, 1, and then that's where I multiply by dy dx. Derivative of 1 is 0. So now, normally what you would have to do is substitute dy dx right here in for dy dx to get it in terms of x and y. But because we're just interested in what's happening with the second derivative at this point, we don't need to do that. We can just go ahead and substitute in the point right away when x equals -4 and y equals -1. Because when we do that, we get 1/2 minus, the reason why we don't have to substitute in is because we already know at this point when you plug it into this part, if we put it here, it just makes it 0. So it's just 1/2 minus 0 gives you 1/2. And the importance of this is whether it's positive or negative. So in this case, 1/2 is greater than 0 positive. And remember, that means it's concave up, shaped like a cup. So if we put these two things together, the slope is 0, slope of the tangent line is 0, and it's concave up, shaped like a cup, like this. That's what shows you it would actually be a relative minimum here, which is the same as a local minimum. If it was concave down, then it would be a relative maximum. So we can say F has a local minimum at x equals -4, or you could say at -4, -1, either way, but it's just worded the same way you worded here. And your justification would be since, and you can just use the notation we used right here. Since the first derivative, dy dx, specifically at x equals -4, y equals -1 equals 0. And the second derivative, d squared y dx squared, at x equals -4, y equals -1, is greater than 0. That would be our answer with justification. All right, let's take a look at part C. This one, a little bit different. And this is the thing that's a little new here. says consider the differential equation here. Find the values of the constants m and b for which y equals mx plus b is a solution. So to be a solution to this differential equation means this is the derivative. So let's go ahead and start this off by actually finding the derivative of this. Remember, m and b are constants, so the derivative of mx would just be m, just like if it was 5x, it would be 5, and the derivative of b is 0. So the derivative is just m, which makes sense because the derivative is the slope. And you can see this is just a linear equation in slope-intercept form, so that's m. Then we know this derivative m has to be this. In order to be a solution, it means this is the derivative of it. So, and this is the original equation, so then we can just substitute this in, 1/2 x minus y plus 1 in for dy dx right here. And that will give us the equation 1/2 x minus y plus 1 equals m. However, we can't solve for m and b yet because notice this only has m in it. It does not have b. So the way you get that b in there is notice we have a y here, right? And remember, we know for this, y is equal to mx plus b. So we can use another substitution and substitute mx plus b. So y equals right in there for y. So then we'll have 1/2 x minus, instead of y, mx plus b in parentheses, plus 1 equals. And then if we distribute out the negative, we'll have 1/2 x minus mx minus b plus 1. So this is the part where we're going to use a little strategy that is not super obvious to help us solve for m and b. Because initially it looks like, well, we've got one equation, we've got three unknowns, m, b, and x. That's going to be tough to solve. So the strategy you can use here is by focusing on the variable part of the equation and the constant part of the equation. So our constants, I'll put over here, and the variables I'll put over here. So let's look at the constants first. That's easier. Notice the constants on the left side of the equation are, well, these aren't constants. They have x in it, but b is a constant, remember, and so is plus 1. So negative b plus 1 is a constant on the left side, and m is also a constant on the right side. So if we set the constants equal, that'll give us the equation negative b plus 1 equals m. If we set the constants equal, and then we set the variables equal to each other. So the variables on this side are 1/2 x minus mx. But notice there's no x's over here. There's no variables. So it's like having 0x over here, which is just 0. So we know that would equal 0. So if the variables are equal on each side and the constants are equal, that'll make this a true equation. Right? So that's what we can use to solve. And then to solve, it's actually easier to solve. We can't solve the constant one yet because it's got two unknowns, m and b. The variables does too, but there's a strategy you can use. Notice you can factor out the x. And we're left with 1/2 minus m. As this is in factored form, one of these has to be 0. So yeah, x could be 0 to make this true. However, we're not interested in solving for x. We're interested in figuring out what m and b could equal. So if we set the 1/2 minus m equal to 0. Whoops. That's 0. That would make this equation true. Add the m over, so m could equal 1/2. So we've solved for m. And then we substitute that right back in here, m, into the other equation, and that allows us to solve for b. So for b, we've got negative b plus 1 equals 1/2. And then you can add the b over to the other side. And then subtract the 1/2 from 1, so you get b equals 1/2 also. So it's just a coincidence that they're the same value. That's not usually going to be the case here. If both of them are 1/2, that would make the variables equal and the constants are equal. Usually you get different values for m and b. But let me show you why this works here. This is a linear equation, right? So what we just figured out is m is 1/2 here and b is 1/2. So if we write that and go back to our slope field that we graphed, what it's saying is y equals 1/2 x plus 1/2 is a solution to this differential equation, which means in terms of the slope field, remember the solution when you graph it fits in the slope field. So it's saying this linear equation would fit in the slope field. And let's confirm that it actually does. So 1/2, that's the y-intercept, would be right there. And the slope is 1/2. And if you notice, it's right in line with these that have a slope of 1/2. So that would give you the particular solution. You don't have to graph it. This just confirms that we have the right answer right along there. You can see it fits right in our slope field, which confirms that is a solution to this differential equation. And that concludes the notes for AP Calculus on the topic of slope fields continued.